Hey there, this is Mr. Wilford, and I just wanted to go through Chapter 6, Section 6 with you, Fundamental Theorem of Algebra. And we've been talking a lot about polynomials lately, and one of the things about polynomials, one of the important things that we want to be able to find are the roots of a polynomial, or the zeros of a polynomial. And when we talk about the roots or the zeros of a polynomial, one of the things we can do if we're given the roots or the zeros is we can find the polynomial that would match with that, or a polynomial that would match with that. So in this example here, we're kind of working backwards here from when we talked about factoring. So we're given the zeros here, -3, 1/2, and 1. So there are 3 zeros or 3 roots that we have. From each of those zeros or roots, we can write the factors. And remember, we can write it as the opposite of the zero. So x plus 3 if we're given the 0, -3. X minus 1/2, x minus 1, and so on. Then what we do is we actually have to FOIL, multiply the first two factors together, simplify it, and then multiply the next factor together and simplify that. And our result here would be a polynomial that would contain those 3 roots, or zeros. Now, this is really where the fundamental theorem of algebra comes in. And you can read that up here, but basically what it's saying is the degree of the polynomial will indicate how many total roots you should have. And this includes real and imaginary roots, and all multiple roots as well. And so when you have a problem like this right here, we look at this and we know that we should have 4 total roots, and we can count the real roots as well as the imaginary roots in there. So let me show you this right here is the same problem. And if you graph this, I would always suggest starting out these problems by using a graphing calculator and plugging this into your graphing calculator, and you get -2 and 1. You can see here from the graph that we have the roots -2 and 1. Remember that our roots would be where the graph crosses the x-axis. Now those are only 2 of them. X equals -2 is one root, and x equals 1 is another root. Those are real roots. Because my degree up here is 4, I should have 4 total roots. So what we're going to do is we're going to take this -2, take one of the roots, and then we use synthetic division. So 1, 1, 2, 4, -8. And you do synthetic division, and you should get out a 0 here. Then what you do, you're going to get a list of numbers down here, and then you're going to take the other root and use that as your corner number, and you do synthetic division again, and you should get 0 down here. Now I'm not doing all of this work here, but I'm just showing you. What happens is you end up getting some numbers down here, and these numbers will be the coefficients of a quadratic, because every time you use one of the roots here as a corner number, every time you do synthetic division, you're knocking the original problem down a degree. Okay, so here we would be at degree 3, and then here we're at degree 2. Once you have a degree 2 problem here, you can either reverse FOIL this to find the other 2 roots. You can use the quadratic formula, or you can complete the square. It's probably a good idea to use the quadratic formula, and you're probably going to get out imaginary roots, especially in this example, because we only see 2 real roots here. Okay, so that's kind of the idea behind all of that part. Then if we go to the last page here, we have another theorem, and this is the complex conjugate root theorem. And basically this is saying that if we know that a plus bi is a root, then its conjugate a minus bi is also a root. So here's an example. 4 plus 3i is a root, then 4 minus 3i must also be a root. So what you can do is actually take roots like this, or zeros like this, and use these theorems, the complex conjugate theorem and the irrational root theorem, and you can actually get a polynomial function with those roots, similar to the previous 2 examples. If you have any questions, please let me know. Thanks.